Ever get that feeling, that one, like we're just starting to, I don't know, scratch the surface of what's really out there.
Oh, absolutely.
And today we're diving deep, really deep into something that's making a lot of astronomers kind of rethink things. Galaxy evolution.
Yeah, it's pretty amazing.
It really is. And we have this new research paper. It's called, get this, JWST reveals bulge-dominated star-forming galaxies at cosmic noon.
Catchy title.
It's a mouthful. But trust me when I say this, the title, it doesn't even begin to cover, like, all the questions that this research, it just throws at you.
It's a wild ride, this paper.
Oh, it is. So get ready, folks, because we're unpacking some seriously mind-bending stuff today about cosmic noon, these massive galaxies, and what the James Webb Space Telescope, JWST, is showing us that, well, Hubble just couldn't.
Yeah, Hubble was pretty good, for its time, but this is next-level stuff.
Next level is an understatement. But okay, let's back up a bit for our listeners who are, just tuning in. But let's talk basics. We're talking huge galaxies here, bigger even than our own Milky Way.
Oh, yeah. These are the big boys.
And we're looking way back in time, like when the universe was still a teenager, a period astronomers call cosmic noon.
Always love that name, cosmic noon.
Right. It's evocative. But what made that time so special in the first place? And what was Hubble seeing that led us to think we had these massive galaxies all figured out?
Okay, so cosmic noon, and this is just a rough estimate. We're talking about a period roughly 8 to 10 billion years ago.
Okay, so way back.
Way back.
Yeah.
And it was like this baby boom for galaxies, just churning out stars like crazy.
Real party.
Oh, yeah. The universe was really living it up. Now, Hubble gave us our first good look at this era, but it was mostly seeing the light from the young, hot stars. And these often show up as kind of messy, disc-shaped structures.
So picture a plate spinning really fast and sprinkles scattering outwards.
Exactly.
Chaotic, but kind of beautiful, too.
Oh, for sure.
So we saw these sprawling disks of young stars and just kind of assumed, okay, that's the whole picture.
Right, like looking at a city still under construction and assuming, well, there's nothing in the downtown yet.
Exactly. But then enter the James Webb Space Telescope, JWST, with its incredible infrared vision. And that's where everything changes, doesn't it?
Oh, it does. Big time. See, Hubble, it mostly sees visible light, right? But JWST, it can peer right through all that dust and gas that obscures those early galaxies.
It's like having a special lens that can cut through a thick fog.
Perfect analogy.
So we get a clearer view. But what's the big aha moment? What did JWST reveal about these galaxies that has everyone so, I don't know, amazed?
Well, the thing is, when we look at these massive galaxies, but in the infrared with JWST, they suddenly look really different.
Different how?
Instead of just those sprawling disks, we're seeing this much stronger concentration of light right smack in their centers. Astronomers call this a bulge.
Hold on. Bulges. Aren't those dense central regions we usually associate with old retired galaxies? Like, they've had their fun, they're done making new stars.
You got it.
But we're seeing them in galaxies that are still very much in their star-forming prime. That's kind of like finding out your teenage neighbor is secretly a world-class chess champion.
I love that. Totally unexpected, right? And that's what this research is all about. It challenges this long-held assumption that a dense central bulge means a galaxy is winding down. It seems these bulges, or at least their precursors, they can form much earlier in a galaxy's life than we ever thought.
So it's not just that JWST sees more, it's that it's seeing differently. It's giving us a whole new understanding of a really important period of galaxy evolution.
Absolutely.
But before we get into all the mind-blowing implications of this, let's dig a little deeper into what the researchers actually observed.
Okay, sounds good.
So the paper, it zeroes in on 70 of these massive galaxies at cosmic noon, right? And they compared the images, Hubble versus JWST. What was it specifically that really jumped out when they looked at the JWST data?
The biggest difference was in something called the light profile of these galaxies.
Okay, and for our listeners who aren't familiar with astronomer lingo, break that down for us, light profile.
Sure. It's basically a measure of how the brightness of a galaxy changes as you move from the center outwards. Imagine you're looking at a city skyline at night.
Okay, I'm picturing it.
Now, in a city with a dense downtown core, where would the brightness peak?
In the center, obviously.
Right, and then it kind of drops off as you move out towards the suburbs.
Makes sense.
So with JWST, it's like they were suddenly seeing this hidden downtown all lit up in what Hubble had just perceived as this sprawling suburb.
Wow. Okay, so to recap, we have these massive galaxies, cosmic noon, a time we thought was all about chaotic young stars, right?
Right.
But JWST comes along, and basically says, hold on, there's a whole lot more to this story.
It did, didn't it?
Suddenly, we've got these dense central regions, these bulges, that totally challenge our understanding of how and when galaxies transition from their, wild youth to a more settled phase of life. It's a real cosmic plot twist.
It really is.
And it raises so many questions about what exactly is going on in those early bulges.
Yeah.
It's like we've been handed this cosmic mystery novel.
Right.
And the more we read, the more we're like, wait, what's going on here?
The plot thickens.
It really does.
Yeah.
So let's put on our detective hats for a minute here.
Okay.
And try to figure out what's really going on inside these bulge information galaxies, as they're being called.
Yeah, what's the deal with these things?
Exactly. The million-dollar question, of course. What exactly is making up these bulges? Is it mostly like old stars hiding in the dust, or are we seeing young stars, still forming but kind of shrouded?
It's a great question. And honestly, the paper itself kind of throws its hands up in the air a bit on that one. We need more research to say, for sure.
It's like trying to figure out what's inside a beautifully wrapped present, but you can only shake it. You can guess, but...
Exactly. You're not going to know until you open it up and take a peek.
Exactly. So where do we even begin to unravel this mystery? What other clues are astronomers looking for?
Well, one key thing is to figure out the ages of the stars in those bulges.
Okay, makes sense.
If they're mostly old, red stars, then that suggests these bulges formed early on, maybe through a rapid collapse of gas way back in the early universe.
Okay, so that's one scenario.
But if we find a lot of young, massive stars in there, that points to a more ongoing process of bulge formation, maybe even fueled by those same star-forming disks we were talking about earlier.
So it's like trying to figure out if a city's downtown is mostly historic buildings or if there's a lot of new construction still going on.
Perfect analogy. And to figure that out, astronomers are going to be looking at these galaxies across a wider range of wavelengths, not just in the infrared with JWST.
So what, like ultraviolet X-rays?
Exactly. Ultraviolet would reveal those very young, hot stars, while X-rays, they could uncover hidden black holes that are gobbling up matter in those cores, which could also be contributing to their growth.
Okay, so it's like using a whole bunch of different detective tools.
Right.
Each one gives you a different piece of the puzzle.
Exactly.
This is amazing stuff, but this discovery, it's not just about these individual galaxies, is it?
No, not at all.
This has some pretty big implications for how we understand, like galaxy evolution on a much grander scale.
Oh, absolutely. This has the potential to really shake up our understanding of how galaxies evolve over, billions and billions of years.
Like, it challenges that classic view, right? That massive galaxies, they go through this kind of abrupt change from being really active star-forming powerhouses to becoming more, quiescent, as you astronomers like to say.
We do love that word, don't we?
It's a good one. But the old idea was that once a galaxy had a big central bulge, it was basically heading towards retirement. Star formation was winding down. But now
it seems like the picture might be a bit more, shall we say, complex than that. These bulge information galaxies are showing us that a galaxy can still be forming stars like crazy, even while it's building this massive central region. It's like, imagine a company that's still super innovative and productive, even as it gets bigger and more established.
Okay, that's a good analogy. It makes me think that the universe, it doesn't always follow our neat little categories, does it?
Rarely. And this has big implications for how we interpret observations of other galaxies, too, near and far. We can't just assume a galaxy with a big bulge is old and inactive anymore.
So we need more information.
We do. We have to look at its star formation rate, its gas content, even its environment. Get the full story.
Speaking of environment, you mentioned earlier that galaxies aren't just randomly scattered out there, right?
Right. They're very social creatures.
They like to cluster together in groups.
Cosmic neighborhoods.
Exactly. Do we have any idea about where these bulge information galaxies are hanging out? Are they in the crowded city centers of these galaxy clusters or out in the more sparsely populated outskirts?
Another fantastic question. And that really gets at how a galaxy's surroundings can actually shape its evolution.
Right. Peer pressure, galactic addition.
Exactly. This particular study didn't actually look at that, galactic environments, but it's definitely something astronomers are, they're really interested in figuring out.
So what are we thinking? What could those galactic environments tell us about how these bulges are forming?
Okay, so let's say we find these bulge information galaxies mostly in dense clusters, right? That might mean that bumping into other galaxies, like mergers, or just close encounters could be triggering those early bulge formations.
So like cities in densely populated areas, they're more likely to have big, bustling downtowns because they're always kind of growing and merging with their neighbors.
Precisely.
Yeah.
But on the flip side, what if we find these galaxies hanging out in the emptier parts of the universe?
Then what?
Then that might mean they're forming those bulges more on their own from internal processes.
So they're building their downtowns from the ground up without needing all that external pressure.
Exactly. It suggests that factors like a galaxy's own internal dynamics, its rotation, its gas content, even things like feedback from supernova explosions within the galaxy, those could all be enough to create that early bulge formation.
So by understanding the environments of these galaxies, we get clues about whether it's more of an inside job or an outside influence that's shaping how they evolve. Kind of like trying to figure out if a tree's growth is more influenced by its genes or by, the climate and the soil conditions it experiences.
I like that analogy.
And of course, just like a tree's growth rings can tell you about what it experienced over its lifetime, the properties of these galaxies, they might have clues about what the early universe was like billions of years ago.
Absolutely. These bulge information galaxies, they're like time capsules, giving us a glimpse into an era when the universe was much younger and very different.
All right, time to put on our cosmic historian hats then. What kind of insights might these galaxies offer about the early universe? It's like we're peeking through this, cosmic keyhole or something,
Right.
trying to get a glimpse of, what was the universe like way back when?
The ultimate history lesson.
Seriously. So what can these bulge information galaxies actually tell us about those early days? What was going on back then that allowed these massive structures to pop up so early?
One of the most interesting things about this whole discovery is that it really challenges how we thought about the early universe affecting how galaxies form.
How so?
Well, for a long time, the going theory was that the early universe was this chaotic, turbulent place
Okay, makes you
with
think
galaxies constantly merging and crashing into each other.
like a cosmic mosh pit.
Exactly. And the thinking was that those collisions, those interactions, were what really drove their evolution, how they changed over time.
So those early galaxies were basically like cosmic bumper cars, constantly bumping into each other, merging, and that's how they got their shape.
Yeah, that was the general idea. But if these bulge information galaxies are telling us anything, it's that maybe, just maybe, at least some galaxies were able to build those big central structures, even with all that early cosmic chaos.
So maybe it wasn't a complete free-for-all. Like maybe there were some pockets of, relative peace and quiet where galaxies could evolve at their own pace more gradually, driven by their own internal stuff.
Yeah. Like imagine, even in the middle of a crazy, bustling city, you can still find those quieter neighborhoods, right, where things move a little differently.
Oh, for sure. That's a great way to put it. So we're getting this much more, nuanced picture of the early universe than we had before.
Definitely.
But that also brings up a ton of new questions, doesn't it?
Right.
I mean, if these early bulges weren't all formed through these big collisions, then what else could have been going on?
That's the million-dollar question, isn't it?
It really is.
One possibility is that those early galaxies were just chock full of cold gas, which, as we know, is the fuel for making new stars.
Right, like the raw material.
Exactly. And this gas, it could have been pulled towards the galactic centers by gravity, maybe even sculpted and pushed around by powerful supernova explosions. And all that would have provided the fuel for those bulges to grow, and fast.
So it's less about smashing together to build a bulge, and more about just efficiently using all the available materials around them, like cosmic vacuum cleaners, just sucking up all the leftover gas and dust from the early universe.
I like that analogy. That really captures it. But there's another intriguing possibility. Dark matter.
Ah, yes, dark matter. The universe's biggest mystery. We can't see it, but we know it's there, pulling the strings. So how could dark matter be involved in shaping these early galaxies?
Okay, so we know that dark matter forms these huge halos around galaxies, right?
Right, like a scaffolding.
Yeah, exactly. It provides this gravitational structure that basically holds everything together.
Okay.
Now, what's cool is that simulations have shown that the way dark matter is spread out in those halos, it can actually influence how those galaxies form and change over time.
So even though we can't see dark matter directly, it's like it's this invisible hand shaping the galaxies from the inside out.
That's a great way to think about it. And it's possible that the way dark matter was distributed in the early universe, together with all that cold gas we talked about, maybe that created the perfect conditions for these bulge information galaxies to, well, form.
Wow.
Yeah.
It's mind-blowing to think about all these forces, visible and invisible, working together to shape the universe as we know it. It really highlights how much more there is to learn, doesn't it?
It really does. Every answer just leads to more questions.
That's what makes it so exciting. Well, as we wrap up this deep dive, I have to say, I'm left with this incredible sense of awe at just how vast and complex the universe is. It seems like every time we think we're getting a handle on things, a new discovery comes along and shakes everything up. But that's the beauty of astronomy, isn't it? The constant exploration, the never-ending quest for knowledge, and the realization that we're just starting to scratch the surface of understanding our place in all of this. Thanks for joining us on this incredible journey. And until next time, keep looking up and keep asking those big questions.